we have spent lots of effort just to get this equality. And as in the book, we'll call this 2.3. Some of you may have forgotten what we are trying to prove in here. Now let me remind you. We are trying to prove that the measure of b is either 0 or 1. Because once that is proved, since b is arbitrarily chosen, we can thus prove that sigma is ergodic. Because our final goal is to prove that the Bernoulli shapes are ergodic. And we have spent a lot of time on A. Remember, in this claim, we approximate B with A, that is a finite union of cylinder sets, whose error is arbitrarily small. Once we have a very good understanding of A, we will have a good understanding of B. And in particular, once we proved that the measure of A is either 0 or 1, we have a very good hope. And in particular, once we proved that the measure of A is either close to 0 or 1, then we can hope that this approximation target, this B, can have a measure that is either very close to 0 or 1, or precisely 0 or 1. We hope that is true by using this approximation. And so far we have made a very big progress. We have proved that the product of measure of A and the measure of its complement is equal to this guy. If this guy can be proved to be very small, to be very close to 0, which means this product is close to 0, then we can hope that either this guy or this guy is close to 0, and thus it follows from the approximation that either mu of b is close to 0 or mu of b complement is close to 0, and that is close to what we want to prove in the end. So let's continue to see what we can find with this equality. Okay, now in order to approximate the measure of the symmetric difference of sigma inverse A with A, which is by this equality equal to the product of mu of A and mu of A complement, we shall use a triangular inequality in measure theory. So this guy is less than or equal to the measure of sigma inverse A, sigma negative m applied to A, symmetric difference with B, union B symmetric difference with A. Actually, this part is contained in this part. That is why we have this inequality. This is just a set theoretical fact, and I believe I have checked something like this before. But anyway, if you don't remember, you can either search in my video or simply just check it by yourself. This is very easy to check. There will be like 4 cases to consider. Anyway, this is not hard. But this right-hand side, by the subadditivity, is less than or equal to the measure of the first guy plus the measure of the second guy. Now, the second part is very small. We have used the approximation because A comes from the approximation. The second part is less than epsilon. That is actually how we define A in this claim. Now how about the first part? I would let you think about it for a while. The first part is not something very fancy. Actually, because B is sigma invariant. This guy inside the parentheses is actually equal to sigma inverse M applied to A spectral difference with sigma inverse M applied to B. And because the inverse map commutes with everything, you can pull sigma inverse M out of everything. Now you're going to use the fact that mu is sigma invariant. This is assumption above everything because we start with a measure preserving system. The measure is always invariant under some given map. Here the measure is invariant under this Bernoulli shift. So this is equal to the measure of A symmetric difference with B. And this is because of the mu is sigma invariant. Okay, now you know that this line is nothing but mu of symmetric difference with A and B, and the mu of the symmetric difference between B and A. This is just twice of this, because symmetric difference is really symmetric. So this is less than 2 epsilon by our approximation claim at the beginning. That is, remember how we got A. A from the beginning is something that already satisfies the symmetric difference with B has measure less than epsilon. Okay, now we are winning. We are going to finish the proof now. Let's call this equation 2.4. Remember the thing that we want to study, which is the measure of B or the measure of its complement. This product is bounded by the measure of A plus epsilon times the measure of A complement plus epsilon. So why do we have this inequality? This is because if you consider the absolute value of the difference between A and B, this, by triangle inequality, is less than or equal to measure of B minus measure of B intersection A, taking the absolute value plus the absolute value of measure of B intersection A minus the measure of A. And the first part is just the measure of B minus A, and the second part is just the measure of A minus B. And this is just the measure of the symmetric difference between A and B. And this is less than epsilon. And the fact that this part is less than this part has the same proof. And now we just multiply everything out. This is equal to the measure of A times the measure of complement of A plus epsilon times mu of A plus epsilon times mu of complement of A plus epsilon squared. And this is less than Remember, the epsilon is less than 1 by our assumption at the beginning. We can always choose the epsilon to be very small. And those two guys are all bounded at 1 because the measure is a probability measure. So the last three terms are just bounded by 3 epsilon. And the first part is bounded by 2 epsilon. So they are bounded by 5 epsilon in the end. But no matter how many times of the epsilon, we just take epsilon to go to 0. So in the end, we will get mu of b times mu of complement of b is equal to 0. So let epsilon go to 0. Then we have the product of those two guys equal to 0. And either measure of b is 0 or measure of b is equal to 1. That proves the ergodicity because b is arbitrarily chosen. This finishes the proof finally.